Hello, this is James Fisher, and I am continuing our discussion with the mole, but I'm going to put it now in the realms of concentration. But before I do that, I want to establish some prerequisites. So, we established that the mole is a universal unit that expresses some particular type of quantity, or it shows the relationships in certain compounds. Or we also established that the mole is directly related to the atom, and we did the comparison with Avogadro's number. If you don't remember Avogadro's number, it was 6.02 times 10 to the 23rd atoms. So before I wanted to do that, I wanted to express certain symbols that are used to express the mole. We have the popular symbol used, which is N, and that is a typical symbol used to represent the mole. And basically, the mole is a relationship between the grams given and the formula mass of the compound. Now, usually the grams are usually experimental, so basically it is through some experiment or reaction that a question may propose a certain number of grams. Usually, when you have reactions, you have a little bit of a substance or grams left in the bottom of a beaker or in the bottom of a tank. And the formula mass, aka the molecular weight, can be found on the periodic table. So if I go to the periodic table and I look up particular compounds, I have to look up the mass of one individual element and count for the amount of times that that element appears in the compound. So for example, if I have C, let's see, if I have magnesium chloride, if we write the chemical formula, we're going to get MgCl2 because magnesium is a +2 ion. It is in group 2. So we have to count for the one magnesium element in the periodic table, and we also have to count for 2 chlorines because it is Cl2. So that's basically how you do it, and you just add up all the masses together, and that gives you the molecular weight. So as far as quotient relationships, I just wanted to quickly express some quotient relationships between the mole, and I proposed a situation where the grams or the state of grams was fixed, and I just kept increasing or decreasing the number of moles or the formula masses to see what would really happen. And theoretically, it turns out that the number of moles increases as the formula mass decreases and the grams remain constant. And that is evident. If you have something smaller on the denominator of something, of course, the number or the product that you get is going to be relatively bigger in size. And the opposite, if the number of moles goes down, the grams goes up and the formula mass stays constant. The number of grams goes up, you see the moles going down. And just as a side note, if you are in the realm of chemical analysis and you have percents can be directly transferable to grams because we are all in the relative state of 100. So if you have 98.76% of a certain compound or a certain element, you're going to have, 98.76 grams of it. And that is called the grams to moles conversion or the moles to percents conversion. And that is a relatively simple table, and we'll go into that more when we do chemical analysis. So I just wanted to talk about concentration now. Concentration is a big part of a regular chemistry class and an AP chemistry curriculum. And concentration is basically how much of a solution has dissolved. So we measure certain units for the concentration just to show how much of something dissolved in a particular solution. Most of the time, it will be water. And one way that we express it is molarity. We discussed this previously before. And I just wanted to introduce some basic solubility comparisons. These are not actual comparisons, so don't quote me on the numbers. This is just for side-by-side analysis. So, for example, if we set a concentration at 1 or a standard at 1, and the molarity or big M / the concentration is less than 1, little is dissolved in solution. And if we have the M number being greater than 1, that obviously the compound is supersaturated, or you have a lot of the compounds dissolving in, I mean, a lot of the compounds being soluble in the water, where you actually have particles left in the bottom of the tank or the beaker. And if the M is equal to 1, you have achieved perfect equilibrium, and we'll talk about that in a minute. And that means that it's soluble and it completely dissolves in this solution. And if something is insoluble, that means a precipitate or solid has formed in the compound. So we have a lot of compounds that are silver-based or mercury-based or lead-based compounds that actually are insoluble in water. And if you actually put them in a solution with something that is soluble, you will see a solid or a color start to form at the bottom of it, which is not good. So in relative discussion between concentrations, before I get to the next video on some the way the mole is expressed in concentration, I just wanted to briefly discuss some comparisons, and I want to go back to the mole versus concentration sheet, and I wanted to briefly talk about the where is it at? Okay. Where is it at? Oh yeah, I just wanted to say that there are many ways to express concentration. Molarity is one of them. There's also parts per million you can discuss. You can also discuss titration, and I'm gonna get to that a little bit in the next video. But molarity is a basic way to discuss the mole with its perspective in it, and I'm going to explain that in the next video. So if you watch the next video, you will get the information. So until next time.